All right, so in the last class we looked at how to tell what the curve would look like when we're trying to graph a function. And we looked at three things. We looked at the original function and what it told us. We looked at the derivative and what it would tell us about the graph. And then the second derivative as well. So we're going to continue that in this lecture. So we're still on section 12.4, curve sketching techniques. So we're going to look at some that are a little more challenging today, and it's the algebra that we're going to want to stay with. So the derivative pieces are a little more challenging in this portion. So just kind of keep that in mind. So we looked at a couple graphs in the last video. Let's look at two more in this one. So let's say that I wanted to graph maybe a function like this, where maybe I don't already have a predetermined idea of what it will be. You know, when it's an x squared function, we know it's going to look like a parabola. When it's a rational function, we kind of have an idea that it might have some asymptotes or something like that. But something like this, we really don't have necessarily a great idea of what it's going to look like. So the first thing we're going to do is we're going to pull everything that we can from the original function itself. Okay. Remember, there's three kind of subparts to this. We ask ourselves, what is the domain? Okay. Remember, domain is what is x allowed to be. Notice there's really no off-limits values for x. We don't have any fractions where we need to worry about the denominator being 0. So when that's the case, the domain is just going to be negative infinity to infinity. In other words, the graph is continuous. We don't have to pick up our pencil to draw it. That's what that part tells us. Part B is we're going to find the intercepts. Remember, we find each intercept by setting the other variable equal to 0. So if we want the y-intercept, we set x equal to 0. If we do that, f of 0 is 3 minus 0, and then e to the 0. Okay, e to the 0, or anything to the 0 for that matter, is just 1. So we end up just getting 3. Okay, so we get a point of 0, 3. Okay. For the x-intercept, or intercepts, we're going to set y equal to 0. Notice in this case, although this function looks a little more complicated, it's actually already factored out for us. It's already in parentheses form, so we're going to take advantage of that. When it looks like this, we just set each part equal to 0. So 3 minus x equals 0, and also e to the x equals 0. So here we're just going to get x equals 3, right? If you subtract 3 from both sides and get rid of that negative sign. But here we ask ourselves, you know, what power of e would give us 0? And the answer is it would never happen. So this is actually not able to be 0. Anything to the 0 power is actually 1. There's actually no power that makes a number 0. So keep that in mind. So here the answer is just 3, 0. Okay, so that's our intercepts. And then lastly, do we have any asymptotes? Remember, vertical asymptotes are found by setting the denominator equal to 0. We don't have a denominator, okay? And horizontal asymptotes are found by finding the limit as x approaches infinity, and we're not going to have that either in this function. So just like if it were a polynomial, there's no asymptotes here. Okay, so that's step 1. We've gathered everything we can from the original function, so step 2 is we're going to analyze the first derivative. Okay, so remember what we do for that. We have to find the first derivative and then set it equal to 0, and also find out if we have any values where the derivative is not defined. Okay, so let's go back up and look at our original function where I'm pointing at with my pen. Notice there's two parts to it, right? So this is a product rule situation. Okay, so we are going to have to set up our template. So it's going to be first times derivative of the second plus second times derivative of the first. So if you have forgotten product rule, this would be a good time for you to kind of go back and review yourself on that. But product rule is what we would have to use to be able to find the derivative of this two-part function, right? Anything with an x in it is its own part, so we have a 3 minus x part to the function, and we have an e to the x part to the function. So it's first, no changes, right, just as it sits, times derivative of the second. Notice the derivative of e, though, is a special type, right? It's just itself. And then plus the second, which is, again, e to the x, times the derivative of the first. The derivative of 3 minus x would just be negative 1, because the derivative of 3 is 0, the derivative of negative x is negative 1. So what we end up getting is this function right here, e to the x times 3 minus x, and then minus e to the x, and we're supposed to be setting that equal to 0. Okay. Now, when we're trying to set this equal to 0, we want this to be factored. And notice if we look at these like groupings, this as a group and this as a group, each of these groups have an e to the x in them. So we're going to pull out the e to the x out of both groups. That will leave 3 minus x here. Okay. If you pull out e to the x from itself, you'll just have 1 left over. Okay, so kind of an algebra trick here. We look to see what they have in common and we factor it out. So the factored form is going to look like e to the x, and then if we combine like terms, 3 minus 1 is 2. So times 2 minus x parentheses. Okay, so now we're ready to set each part equal to 0. But just like we had a minute ago, remember this can never be 0. E to the x is never 0. Okay, but we do get an answer here of 2. Okay, and remember what the meaning of this 2 is. This is what we call a critical value. It's what makes the first derivative 0. You're going to put this on your number line. Okay, if you remember what the sign chart looks like. So let's sketch us a sign chart. We're going to sketch a sign chart. We're going to mark 2. We're going to indicate that 2 gave us a first derivative of 0. And then we're going to try to determine what's going on here and what's going on here. Okay, and we do that, remember, by choosing test points. So the test points I would probably pick are maybe 0 to the left of 2, maybe 3 to the right of 2. Remember what you do with these for the first derivative sign chart is you plug these into the first derivative. Okay, so I would plug them in here. Probably all you need to do is determine whether or not you get a positive or negative result here. If you plug in 0, you're going to get a positive result. So we'll put a plus sign up here. If you plug in 3, you're going to get a negative result. So we'll put a minus sign here. Notice 2 minus 3 would be a negative. That's why we get a negative there. So we have part of what step 2 tells us. We know that we are increasing from negative infinity to 2. And then we know we are decreasing from 2 to infinity. Okay. We also, though, know that there's some sort of extrema here, okay, where I'm pointing with my pen. Notice we change from positive to negative, right? We change from increasing to decreasing, which means there's a max right here. So all we need to do is actually figure out what that max point is. So we are going to need to do f of 2. Remember, to find the y, you always plug it back into the original. So we're going to do 3 minus 2 parentheses, and then times e to the 2. Okay. So if you wanted the exact answer, it's e squared. But if we take our calculator and figure out what the meaning of e squared is, or what the approximate value is, we would do e to the power of 2. Okay, notice it's about 7.4, right? We're going to need that when we get to the graphing portion. So we would say, yeah, it's about 7.4, okay? But as far as where is the relative max, I'm going to list the exact answer. The relative max is at 2 comma e squared, okay? If MyMathLab wants you to use a rounded version, it'll say that, and then you would say 2 comma 7.4, okay? But this is actually a more exact answer. All right, so that's step 2. I analyzed everything I could about the first derivative. So now the final step before I get to the graphing of all this stuff is to analyze the second derivative. So before I do that, let's rewrite what the first derivative was. Okay, and I'm going to rewrite it in its most simplified form. Okay, so remember this was the first derivative, right? What I want is the second derivative. So once again, notice I do have 2 parts, just like I did at the beginning, right? So I am going to need product rule again. So we've got first times derivative of the second plus second times derivative of the first. So the first is e to the x. The derivative of the second is -1. The second piece is 2 minus x. The derivative of the first is e to the x. So for the second derivative, which remember I'm trying to set equal to 0, I get negative e to the x and then plus 2 minus x parentheses e to the x. Okay, and I'm supposed to be setting that equal to 0, which again means I'm going to want this in factored form. So just like I kind of did above, notice this looks similar to the first derivative as far as the format looks, right? So I'm going to pull out what they have in common. So this time I'm going to pull out an e to the x. Okay, and so if I do, I get -1 here, right? If you divide negative e to the x by itself, you get -1. If you pull the e to the x out here, you're going to get just the 2 minus x parentheses left over. So we want this in factored parentheses form. And notice if you combine -1 plus 2, you get 1. So I end up with two pieces once again, where I can set each of them equal to 0. But notice one more time, this can't happen, right? We can't have e to the x be 0, so I don't get any values there, but I do get a value here, right? I get x equals 1, okay? And remember, this goes on your number line. It's not a critical value because we're talking about second derivative now, but it is a value that is supposed to show up on our number line. It is an important value that we have to mark. So here's 1, okay? We're going to write 0 above, right? But this time we're plotting or deciding what happens with the second derivative. So again, I have two sections to test here, right? So I am going to want to choose test points. But this time I'm going to plug them into the second derivative. So I would probably pick test points maybe of 0, maybe 2. Okay, so if you plug in 0 here, you're going to get a positive. If you plug a 2 in, you're going to get a negative. Okay, remember with second derivative, it determines concavity, so now we know that the graph is concave upward first from -infinity to 1, and it's concave downward after that from 1 to infinity. Okay. One more thing the second derivative, remember, tells us is if we have a sign change, as long as it's defined at that value, then we actually do have an inflection point. So kind of like we did for that max in step 2, we're going to need to find f of 1, okay, going back to the original function itself. So if you plug that in to the original function, it's going to look like 3 minus 1 parentheses and then e to the first. So if I wanted an exact answer, it would be 2e. But if I want a simplified, maybe decimal type answer, it's going to be about 5.4. You can just use your calculator for that. So we have an inflection point, and the inflection point is at the point 1 comma 2e, or again, if my math lab wants decimals, then you would say 1 comma 5.4. Okay. All right, so last but certainly not least, this is what we were getting to. We want to graph all the info we just found kind of painstakingly, right? So we're going to sketch us a graph. I'm going to go out 8 in every direction. I'll go out further if I need to. So far, the biggest value I had was 7 point something, so I think 8 will be enough. Okay. And we're going to plot all the information we know. Okay, so we're going to start at the top. We're going to plot any intercepts we have, right? Which we know we have a y-intercept at 3, and we know we have an x-intercept at 3. Okay, here is the point where we would mark asymptotes if we had them. We don't. Okay, we have a max at what? We have a max at 2 comma about 7.4, so maybe about here-ish. And I always mark this as the max because that tells me, hey, I don't need to go any higher than that. I also have an inflection point at about 1 comma 5.4. So that's a significant value also. So maybe about here-ish. So I'm just going to label this as IP for inflection point. Okay, and then we know some things, right? So I'm going to use my concavity. I know that coming from this inflection point, I'm supposed to be concave downward on this left piece. I'm supposed to be concave downward. Okay. Now I do know that I'm supposed to be concave upward here, but what I don't know is like watch my pen. Does it go concave upward like this, or does it cross the x-axis and go up? Does it go up immediately? Like there's some stuff we don't know, right? So here is where we pick additional points if we think we need them, and I don't think we need many, but I do think we need some additional points to know what's going on in this graph. In my opinion, we don't really need anything over here. We already kind of sketched that, right? I already have these 2 points, so maybe I can pick some points over here. I'm going to pick -1 and -2. And you can even use your graphing calculator to figure out what those values are, and I would. Like, plug in the original function and then use the table function, or the table feature. But if you plug in -1, you get about 1.5. If you plug in -2, you get about 0.7. And I think that's going to be enough to kind of give us a good idea of what the graph is doing over here. So if I plot those values, and I make sure that I make this concave upward, kind of like this, then I think we're good there, right? Notice you can always kind of side by side it and check and just plug the original function in and see, did I get a good idea of what the graph is? Did I miss something? So let's enter in the original, 3 minus x, and then e to the x. And let's see how close our sketch is to what the actual graph looks like. Okay, notice the general shape's pretty darn close to what we have, right? So our graphing calculator is kind of our backup tool to decide, did we get a good idea of the graph or not, okay? And I've said it before, but the only way you're going to know which additional points to pick, kind of where I'm pointing here, is to graph what you have, right? We had to see, where do I know what the graph is doing versus where do I not really know for sure what the graph is doing. That's how you decide what additional points to pick, if any. Okay. All right, so let's do one more. Clearly, these are lengthier type problems, so just keep in mind when you're doing your homework that you need to leave yourself enough time to complete these. So let's say that I wanted you to graph the following. F of x equals 2x over x squared minus 9. Okay, so let's run through our steps. So step 1. Analyze the original function. Okay, so this will be a good practice because there's actually some pieces to this function that there wasn't in the previous problem. So step A is to find the domain. We do have some issues with the domain here, right? What do we not want to happen with domain? We don't want the denominator to be 0. And notice it can be 0, right? If we factor this out, it's just a difference of squares. We get x plus 3x minus 3, can't be 0. Okay. In other words, x can't be positive or negative 3. So if you're asked to do this in interval notation, remember you can do it kind of like this. I have a number line and I want to kick out -3 and 3, but I want to include everything else. Okay. So if you're asked to write this in interval notation, it would look like -∞ to -3, not including -3, -3 to 3, not including either, and then 3 to infinity. Okay. All right. Part B is to find any intercepts, if we can. Okay, so first let's start with the y-intercept. We always remember set x equal to 0 to find the y-intercept. So we would find f of 0. So we get 2 times 0 on top over 0 squared minus 9. So we end up getting 0 or just the point 0, 0. Okay. For the x-intercept, we'll set y equal to 0. So 0 equals this fraction. That's a 2 there, sorry. Remember when you have a fraction equal to 0, this will come into play a little bit later. We only care if the top is 0. That's how we make a fraction equal to 0. So we set the numerator equal to 0. Notice if you set 2x equal to 0, that happens when x is 0. So again, we just get the point 0, 0. So notice the x and y intercepts are not distinct points from each other. They're actually one and the same, okay? And that's okay. That happens sometimes. Part C of the first step is to find any asymptotes. And we are going to have some in this function. So I'm going to quickly run through these. You might need to review yourself on how to find asymptotes. But we find vertical asymptotes by simplifying and then setting the denominator equal to 0. In this case, we cannot simplify this at all. Like, nothing really can be done other than to factor the top if we'd like, the bottom. So the bottom factors into x plus 3x minus 3. Notice there's no cancellation or anything there. So the vertical asymptotes just end up being x equals 3 and x equals -3. So we have 2 vertical asymptotes in this function, 3 and -3. Notice you always write vertical asymptotes as x equals numbers. To find horizontal asymptotes, again, this might have been a minute for you, but you need to find the limit as x approaches infinity or -infinity of your function. And remember, infinite limit problems that involve fractions have you put every term over the highest power x in the denominator, which happens to, in this case, be x squared. So I'm going to put this over x squared. and both terms on the bottom over x squared. So we end up getting the limit as x approaches infinity, if you simplify everything, of 2 over x over 1 minus 9 over x squared. Okay, and then remember these go to 0. So this is just kind of a review of things we did before. So you end up with 0 over 1, or just simply 0. So the horizontal asymptote, remember, is written as y equals a number. Okay, so we have 2 vertical asymptotes and 1 horizontal asymptote. Okay, so that takes us through step 1. So now we move on to step 2. This is where we're going to need to have our derivative skills in check here. So we want to analyze the first derivative. So notice the original function looks like this. Okay, so we're going to need quotient rule to be able to do the derivative here. So we're going to need that format, right? So it's bottom times derivative of the top minus the top times the derivative of the bottom. The derivative of x squared minus 9 is also x, or 2x, I mean. And then over the bottom squared. Don't forget that part. So if you distributive property and you clean up everything as much as you can, and that's what you'll want to do, you're going to get 2x squared minus 18 and then minus 4x squared over the denominator. So you end up getting negative 2x squared minus 18 over the denominator squared. Okay, remember what we're supposed to be doing is 2 things. Setting this equal to 0, I'm going to squeeze it in there, but also finding out any off-limits values. Okay, so remember, if I want to set a fraction equal to 0, I just need to set the numerator equal to 0. So I just need to do negative 2x squared minus 18 equals 0. Okay, so a couple of ways I can do this one, but I'm going to do it this way. I'm going to add 18 to both sides. Okay, I'm going to squeeze this in. Notice that gives me negative 2x squared equals 18. Then I'm going to divide both sides by negative 2. So that's going to give me x squared equals negative 9. Okay, notice if I try to take the square root of both sides, I'm going to get non-real numbers. Okay, which means that the numerator is never 0, okay, for any non-real number. Okay, so what it means is the numerator cannot be 0, okay, unless I have something quirky like an imaginary number, and I'm going to assume that I don't. So since the numerator cannot be 0 for any real number x, okay, then I focus on the second part of critical values, right, which means maybe I have a point that's off limits. Well, I've been talking about those already, right? I talked about them when I discussed domain and when I discussed asymptotes. Notice that x cannot be those 2 things that would make the denominator 0, right? It can't be plus or minus 3. So that means these values, although they're different, these are critical numbers. Okay, and these are going to show up on my number line. So I've got negative 3, and I've got 3, but I'm not going to put 0 above these because they're not defined, right? So I'm going to put ND, and then I'm still going to need a sign chart here because I need to know what's happening here, here, and here. Notice this time I have 3 sections to test. So I'm going to choose some test points. Okay, remember what I'm doing with those test points. I'm going to plug them into the first derivative. So the test points I would probably choose are negative 4, probably 0 in between, probably 4 on the right-hand side. So go back up to the second derivative, okay, which, by the way, is this right here, this ugly mother right here, okay? So you would probably put that in your calculator, I would imagine, okay? But if you plug that in your calculator, you're going to find that you actually always get a negative response. It's negative all the way down. So what that means then is that the graph is always doing what? It's always decreasing. So we're going to say that it's decreasing then from negative infinity to negative 3, from negative 3 to 3, and then from 3 to infinity. Okay, Something else that this constant decrease means is that we actually don't have any relative extrema. Notice if you go over there to the sign chart, right, we don't ever change from negative, which if you never change from positive to negative, you cannot have an extrema. Okay, so that's as far as we can get with the first derivative. Notice that was a little tougher, but it really didn't tell us everything about the graph, right? It really just told us, hey, this graph is always decreasing, okay? Helpful information to know, but probably not enough to, by itself, tell us what the graph looks like. Okay, so step 3 is to analyze the second derivative. Okay, so because it's not on screen anymore, let's write down what the first derivative is, because remember, I'm going to have to take the derivative of that to be able to figure the derivative another time. So here's the first derivative. So the second derivative, as much as we hate it, is going to require another quotient rule. Okay, so it's going to be bottom times derivative of the top. So let's just start there. So bottom looks like so, right? Looks like this. Times derivative of the top. Don't overthink it. The derivative of the top is the easier derivative to find, right? So the derivative of the top would be negative 4x. And then it's minus the top as it is times the derivative of the bottom. This is the toughest derivative we have here, right? So the derivative of the bottom is going to require chain rule. So we move the 2 to the front. We keep the inside here the same where I'm pointing. And then we also multiply by the derivative of that inside, which is 2x. And then we put it all over the denominator squared. Notice that since it was squared and we squared it again, it's actually to the 4th power. Okay, so I don't think I have to tell you that this looks like a little bit of a mess. Okay, so there's some different ways you can do this. You can FOIL this out and distributive property through the -4 and all kinds of stuff. Or you can notice that every group has an x squared minus 9 parentheses in it, at least one, right? This one has 2. This one has 4, this one only has 1. So I'm going to start there. I'm going to get rid of 1 x squared minus 9, leaving 1 here, and leaving 3 here. Okay, this is just going to be a little bit quicker way to simplify this kind of mess that we have here. So this is what we have left if we mark out an x squared minus 9 out of everything. We've got, I'm going to simplify these. So 2 times 2x, and then the minus, we've got minus 4x. And then times negative 2x squared minus 18. And then all over x squared minus 9 cubed. Okay, so notice I got rid of what this piece was, right? So all I did was 2 times 2x, which was the 4x, and then just really wrote everything else. So now if I kind of distribute, I kind of didn't want to do that all in one step. So if you distribute here and here, you're going to get negative 4x cubed plus 36x for this distributive property. And then here you're going to get plus 8x cubed and then plus 72x. And then over the denominator, which is now cubed since we got rid of one of them. So if you combine like terms, you get 4x cubed plus 108x over the denominator. Okay, so maybe, you know, pause the video, take a breath, right? That was admittedly ugly, okay? But we want to remember set this equal to 0. But again, we really only care if the numerator is 0. We're trying to find out what makes the second derivative 0, okay, but also anything that's off limits, which we'll talk about it again in a minute. So I really just need to set 4x cubed plus 108x equal to 0 and try to factor and do anything I can. So I can pull out a 4x or factor out a 4x, and that'll leave me with x squared plus 27 equals 0. So now I can set each of these parts equal to 0. Okay, notice here I'm going to get x equals 0. Here, this is never going to happen. If you subtract 27, we had one kind of like that a little while ago in another part of the problem. If you subtract 27 and try to take the square root, you're going to get a non-real answer. So I'm just going to write that. Non-real x, which means it doesn't ever work. Okay, which means this is the only thing that's going to show up on our number line as far as what makes it 0. But then also remember, we still have the off limits values, right? X still cannot be plus or minus 3 because it would still make the denominator 0. Okay. All right, so let's put all of that together in our sign chart, and you got to make sure your sign chart looks good. So we have 3 values that show up on our number line. Okay, if we want to, we can write up here, this also shows up on the number line, right? Just differently, right? This has a 0 above it, whereas these are not defined. Okay, remember, we're tracking what's happening to the second derivative now. Okay, so we have 4 sections to test. Okay, we have 4 test points we'll need also. We need a point in every section. And what are we going to do with these points? We're going to plug these points into the second derivative. So I would probably pick -4, maybe -1, maybe 1, and maybe 4. Okay, we're plugging all of those into, I'm going to move this down a little bit, this up here, right? All of those into the third derivative there. So if I were you, I would definitely use my calculator to kind of give me some guidance there. I get a negative here, I get a positive here, a negative, and a positive. When I plug these guys all into the second derivative, that's what I get. So we have this pattern of negative, positive, negative, positive. So let's talk about what that means, and then we'll discuss any inflection points we have. So that means we are concave downward from -infinity to -3, and also from 0 to 3. If we look at our sign chart we just made, remember, a good sign chart tells you all the information you need, right? Concave upward from -3 to 0, but then also from 3 to infinity. Okay, so it changes concavity a few times. Okay, so let's talk about where it changes concavity. It changes here, but notice this can't be an inflection point because it's not defined. It changes again here. This is a defined point. So this looks like this actually is an inflection point. It changes again here at 3, but that's not defined either. So it only is going to have one inflection point, but last but not least, we need to find out what is f of 0 to find out what the full point is. Okay, so go back to the original. It would be 2 times 0 over 0 squared minus 9. So we just get 0. In other words, not only is this 0, 0 the x and the y intercept, it's also a really important value where we make a turn called the inflection point. Okay, so all of that was leading to step 4, right? Where we graph all the info we have and we ask ourselves, do we know enough about the graph? Or are there some gaps we could know a little more about? And so on and so forth. So let's go ahead and figure out what this graph is. So we'll go out maybe 5 in every direction. I don't know that we need to go out super, super far. We don't really have any big numbers that I remember. Okay, so let's start at the top. We have 0, 0 is both the x and the y intercept. Okay, we do have some asymptotes, so we need to draw those now. So we had asymptotes at -3, but also at 3. And then we said that y equals 0 was also an asymptote. In other words, the x-axis rather is an asymptote. Okay. We also know that this is an inflection point, so I'm just going to mark this as IP. But notice that's like all we have. Okay, like we know some concavity, we know the graph always decreases, we know where it changes concavity, but as far as points go, this is it, because this ended up being kind of a lot of different things. So when we go to find additional points, we're gonna need some here. I mean, we're gonna need to know what is this graph doing in some different spots. Okay, and I'm gonna show you, in case you don't know, how to use the table feature in your calculator. It'll save your life here. So I need a lot of points, notice. I need to know what it's doing in lots of different places, okay? I need to know what it's doing over here, probably at -5 and -4, okay? I need to probably even know what it's doing here, maybe at -2, -1. I need to know 1 and 2 probably. And then on this other side, I need to know 4 and 5. Notice I'm asking you to list a lot of points because I just didn't get a lot of information from this graph, okay? So let's go to our calculator, okay? So when you enter it in, notice I already kind of pre-entered it in for you. Notice that you need parentheses around the top and the bottom, but rather than look at the graph, I'm gonna look at the table because the table will nicely tell us what the values are everywhere. So notice at -5, it's supposed to be negative 0.625. At -4, it's negative 1.1. At -2, it's not negative, sorry. It's just 0.8. -1, it's 0.25. At 1, it's negative 0.25. At 2, it's negative 0.8. 4, it's positive 1.1. And then at 5, it's 0.625. So if you pay attention, we actually have some repeat values. They're just both positive and negative. So then I would say just take a little bit of time and see if you can graph what this looks like, right? So maybe even pause the video and see if you can see what it's doing. Notice here, I know this piece has to be concave upward. And actually, sorry, up here, let's go ahead and change that. I think I had it backwards here, where it's concave upward and downward. Nope, never mind. Sorry about that. I just didn't graph correctly. So that's a much easier fix. Sorry about that. -5 should have been down here. So ignore what I just graphed. It'd be about like this, right? So actually this piece is supposed to be like this. And now it fits what I thought. I was looking at it like that doesn't look right. So this piece is supposed to be concave downward. Okay. -2, it's going to be kind of like this, right? At -1, it's 1.5. So it looks like this piece kind of does this and goes up. Notice everything's supposed to kind of hug these asymptotes, so you can kind of figure that there. At 1, it's supposed to be negative 0.25. At 2, it's supposed to be almost down here, so it looks like this piece kind of does something similar, but in the downward direction. And then last but not least, it looks like these are positive, and that's where I had messed up before. So it looks like they're going to look like, if you graph all of these points separately, and again, if you need to pause the video, then do that. But then notice this piece is going to be concave upward like we said. Okay. In fact, if we want to, we can see that this piece is also concave upward, right? Whereas at 0, 0, it changes to concave downward. Okay. So in this case, not in all graphs for sure, but we needed a lot more points to be able to determine what the graph is. Okay. So just keep in mind, you know, these 4 graphs that I've given you, the 2 in this video and the 2 in the video before it, should really give you kind of a good taste of what different graphs can possibly be. And remember, my goal for you is for you to be able to show me using algebra and calculus what the graph is going to be before you punch it in your graphing calculator. And then if you'd like to verify that using your graphing calculator, then so be it.